Welcome to another video in our high school chemistry series. This one's about measurement. We're going to talk about volume, temperature, and mass, just to kind of work through how to use some of those instruments. The first we're going to talk about when you're reading volume of a liquid. You read from the bottom of the meniscus. The meniscus is the curved part right here that you can see. The meniscus is formed because of the attraction or lack of attraction between the liquid and the walls of that cylinder. So you always want to read from the bottom of that meniscus. Usually that meniscus is going to be curved downward because most of the solutions we work with are water. There's a few exceptions to that, like mercury, where it actually curves the other way. You still actually read from the bottom of that meniscus. So one of the other things is to avoid parallax errors. A parallax error is when the meniscus or a needle from an instrument is viewed from an angle rather than straight on. So for this example, if you're reading a meniscus by too far down on a burette, you'd actually read the measurement wrong, whereas you really need to be straight on. Sometimes that involves moving the instrument that you're working with, or it involves standing on a stool or something like that. So graduated cylinders, it's a graduated cylinder, it's a volumetric measurement, so it's actually how much it contains, and the marks indicate the volume, so you always read from the bottom. That plastic little thing on it is actually a bump protector. It actually prevents breakage as it falls down. It took me 15 years to realize that's what those were for. Volume. Determine the volume contained in a graduated cylinder by reading the bottom of the meniscus at eye level. You always want to read the volume using all certain digits, which is everything you can read that's on the graduation. So every line has a reading. All of those are certain. You're then going to do one uncertain digit. So you want to estimate right in between what those digits are. So the certain digits are determined by the calibration marks. Again, uncertain digits, the last digit is estimated. So let's look at an example. So if we use this, we know for sure it's above 50 and below 55. We are actually below 53, but above 52. So we know for sure it's 52 point something. We just don't know the something, and so that's where we start estimating. So 52 is known. We then start to divide it out. Something like 0.8 milliliters, 0.7 milliliters, any of those would be good estimates. So that last digit's going to vary depending upon who's actually doing the reading of the instrument, but that's why it's called an uncertain digit. So for this graduated cylinder, 52.8 milliliters or something like that. All right, so now let's try. It's your turn. This is a 10 milliliter graduated cylinder, and so I'd like you to pause the video and figure out what that is. All right, so we know for sure it's above 6 and below 7. We can actually see that 7. So we can see the 7 right here. We can see that we're above 6. And actually, if there's 5 graduations between 6 and 7, so it should be 6.2, 0.4, 0.6, 0.8, and then 7. So we are 6.6. Right at the 6.6. We're actually probably just above that. So it should be 6.62, 6.61. I'd even take 6.60. All right, try this one. What's the volume of this liquid in this graduated cylinder? This is a 25 milliliter graduated cylinder. So above 10, below 15, I would actually say we're above 11. So if you look, you go 10, 11, 12, 13, 14, 15. So each of these slightly larger lines is 1. So 11, and we're right at about 11.5. So that's our estimated digit, is that 0.5. What about this graduated cylinder? It's a 100 milliliter graduated cylinder. Again, above 50, below 55. Say it's somewhere near 52.7. All right. Examine this one. Let's see where you get. 76.0, 0.1, Any of those I think would be good, maybe 0.2, but probably 76.0, 76.1. Thermometers are read very similar to a graduated cylinder. Again, you're going to determine the temperature by reading the scale on the thermometer at eye level. Some thermometers are every 0.2, some are every 0.1. It just depends on your thermometer. You read that temperature again with all certain digits and one uncertain digit. Certain digits are determined by the calibration marks, and the uncertain digit is an estimate, same as with our graduated cylinders. Most thermometers encountered in a general chemistry lab, the 10th place is the uncertain digit. This is most of the time. When you're measuring, you don't want to let the thermometer touch the bottom or the walls of a flask or whatever you're measuring test tube. The reason for that is if it touches it and it's on a hot plate or in an ice bath or you're adjusting the temperature, usually if you're measuring the temperature of something, it's because you're trying to shoot for something specific or you're trying to understand it. If you're touching the sides of the wall, you're actually going to be measuring a different temperature than the bulk of the liquid that's in that, because you're going to be measuring the temperature as the temperature of the walls of that flask or the bottom of that flask instead of the liquid itself. So let's look at the one on the left. The one on the left says it is your turn. 87.4, 87.5. All right. On the right. This one I really think is 35.0 or something really close to 35.0. All right, there's triple beam balances. I'm going to tell you most of the time in a chemistry lab nowadays, you're not going to be using a triple beam balance. You're going to be using a digital balance because digital balances are actually now cheaper than a good triple beam balance and can do more work. But just in case, a lot of these rules apply. To protect the balance, these are some of the rules. You should always check that the balance is level and zero before using it, or it'll give you a bad result. Never weigh directly on the balance pan because it contaminates it. You want to put a piece of weighing paper or weigh boat or something like that to protect it. Don't weigh hot or cold objects. They actually change the result, and some of them can be hot or cold enough to actually cause some damage to the balance itself. Clean up any spills around the balance immediately. You don't want those electronics or the physical components to degrade. All right, determine the mass by reading the writers on the beams at eye level. Read the mass by using all certain digits and one uncertain digit. There is a theme here. The uncertain digits, the last digit of the reading is estimated. On our balances for a triple beam balance like this, it's the thousandth place is uncertain. If you're working with a digital balance, it estimates the last digit for you. Whatever it shows you is your certainty. So you'll just write down what's on it, assuming you zeroed it and did all of those things like you're supposed to. All right, so determining the mass, you place an object on the pan. You move the writers along the beam, starting with the largest until the pointer is at the 0 mark. So check to see that the balance scale is at 0. So you read the digits as you go. For this one, 100 in the hundredths place. We have a 10. We have a 4. And then it looks like we're above 0.4. Let's zoom in on that. So I would say 4.9. And then that last digit is probably something like a 4 or 5 or a 6. So 4.97 seems like a decent guess.